Hello, everyone. Welcome back to our Finite Element Method lecture series. In the previous lecture, we learned about mesh refinement, element connectivity, and the importance of local and global coordinate systems. Now that our finite element model has been created, the next step is to define how the structure is supported and how external loads are applied. This is done using boundary conditions, or simply BC. Boundary conditions are the constraints or prescribed actions applied to a structure. They define how the structure behaves at its boundaries. Without proper boundary conditions, a finite element problem cannot produce a unique and meaningful solution. There are three main types of boundary conditions. The first is the displacement boundary condition, also called the essential boundary condition. Here, the displacement is specified. For example, if one end of a bar is fixed, its displacement in the x direction becomes ux equals 0. These known displacements are directly imposed in the system of equations. The second type is the force boundary condition, also called the natural boundary condition. Instead of specifying displacement, we specify the applied force or distributed load. These loads become part of the global load vector in the finite element equations. The third type is the mixed boundary condition, where both displacement constraints and external loads are applied together. Most real engineering structures are analyzed using mixed boundary conditions. These boundary conditions are represented through different types of supports. A fixed support prevents both translation and rotation. A pin support prevents translation but allows rotation. A roller support restrains movement in one direction while allowing movement in the other. A free end has no constraints. Now let's see how boundary conditions are applied in the finite element method. First, identify the prescribed displacements. Next, modify the global stiffness matrix and the load vector. Then, solve the system of equations for the unknown displacements. Finally, calculate the support reactions. The finite element equation, k multiplied by u equals f, or k times u equals f, is solved only after all the boundary conditions have been correctly applied. Let's understand this with the simple bar element shown here. The left end is fixed, so the displacement at node 1 is u1 equals 0, while a force p is applied at node 2. After solving the equations, the displacement at node 2 becomes u2 equals pl divided by ae, which is exactly the result obtained from strength of materials. This shows that the finite element method is consistent with classical structural analysis. So remember, essential boundary conditions specify known displacements. Natural boundary conditions specify applied forces. Together, they ensure a stable and accurate finite element solution. Now that all the components of the finite element model are ready, the next question is, how do engineers perform an entire finite element analysis from beginning to end? Let's understand the complete workflow.
Finite element analysis is not just about creating a mesh or solving equations. It is a systematic sequence of steps that converts a real engineering problem into reliable engineering results. Let's go through the workflow one step at a time. The first step is problem definition. Before creating any model, we must clearly understand the engineering problem. We identify the objectives, decide what outputs are required, make suitable assumptions, and simplify the problem wherever possible. Once the problem is clearly defined, we move to pre-processing. This is where the finite element model is created. We define the geometry, assign material properties, choose the appropriate element type, generate the mesh, apply the boundary conditions, and finally specify the external loads. After pre-processing, the model is ready for analysis. The third step is the solution stage. Here, the finite element software assembles the global stiffness matrix and solves the governing equation, Ku equals F, to calculate the unknown nodal displacements and support reactions. Once the solution is obtained, we move to post-processing. This is where we interpret the results. We examine displacement plots, stress contours, strain distributions, deformation patterns, and other engineering outputs to understand the structural behavior. But obtaining results does not mean the analysis is complete. The next stage is validation and verification. Here, we check whether the model is accurate by comparing the results with theoretical calculations, experimental observations, or design standards. If required, the mesh or model is refined and the analysis is repeated. This iterative process continues until acceptable accuracy is achieved. Finally, we reach reporting and decision-making. The complete analysis is documented, engineering conclusions are drawn, and the results are used for design, assessment, or future reference. Notice the circular diagram shown below. Finite element modeling is often an iterative process. If the results are not satisfactory, engineers modify the model, improve the mesh, and solve it again until reliable results are obtained. The poster also highlights several important modeling checks. Always verify the geometry. Check mesh quality. Ensure that loads and boundary conditions are correctly applied. Verify material properties. Finally, examine whether the results are physically reasonable. Remember, A good finite element model is not just about using powerful software. It is about understanding engineering principles, making correct assumptions, and carefully verifying the results. This chapter has provided the foundation for everything that follows in the finite element method. In the next chapter, we will begin developing the mathematical formulation of one-dimensional finite elements, where we will derive the stiffness matrix of a bar element step by step. That brings us to the end of Chapter 2. I hope this chapter has helped you build a strong understanding of the basic concepts of finite element modeling. If you found this lecture helpful, please like this video, share it with your friends and classmates, and subscribe to the channel for more lectures on the finite element method and structural engineering.